So we kind of have a new functional group with this chapter. So benzyl. What is a benzyl group or a benzyl system?
Isn't it just like the benzene with one lack of a hydrogen?
So not one lack of a hydrogen. Think of the substituent that's going to be on there. So instead of a hydrogen, we're going to have another methyl group. So do you mean a lack of a hydrogen on that methyl group? Like this?
Yeah.
Okay. Sorry. Wasn't sure if you meant just like hydrogen off of the ring.
Oh, no.
Okay, yes. So why is it important that we're talking about what's allowed to move through here when we remove the hydrogen? Electrons, yes. So because we have another alternating double single, we can have electron movement throughout, which adds what kind of stability? Resonance. Good. Why? So it mentions the fact that it's easy to break one of these benzyl hydrogens off. Why do you think it might be fairly easy to do that?
Because the bond is weak.
Why is the bond weak?
Because it's not like one of the stronger forces holding it together. Like not a dipole.
So be careful, those are intermolecular, so those are forces between molecules, not forces within a single molecule. I like where you're thinking though. I'll give you a hint. This has to do with properties that you learned when you were talking about ring activation and deactivation. When we're talking about a methyl group, so if this is our, is this an activator or a deactivator? It's a weak activator, right. So where are the electrons going? Into the ring or out of the ring?
Into.
Right. So if electrons are flowing into the ring, that's going to make those bonds weaker. Okay, so which means it's going to be more readily disassociated from the carbon.
That means it's more acidic, right?
Yes. Okay, let's see here. So then we have benzylic halogenation. Based off of the name, what do you think is occurring in this reaction?
Halogen group is added.
Added where?
That methyl group?
To this methyl group, exactly. So this is where the addition is going to happen, not on the actual ring. Okay, very good. I think the important point here is talking about the intermediate. So essentially, like in Dr. Cosper's notes, she gives two different examples. So you have it with bromine where only one halogen is added. But if you do the same reaction with chlorine, you end up with 3 chlorines. So there is a note, and it doesn't necessarily say whether it would happen with all the halogens, but So this is what happens when you have an excess of halogen. So we have multiple halogenations happening. In this process, you have an intermediate that's not being shown, and this intermediate is very stable, which is why this is a very stable and spontaneous reaction. And that stability comes from resonance, okay? So something you already know, but it's explaining why this reaction is taking place. Okay. Any questions on halogenation? Nothing too crazy. These can also undergo SN1 and SN2 reactions. So when you have an SN1 reaction, do you have an intermediate or a transition state forming in that reaction? Intermediate, right, because it's a stepwise reaction. What specific type of intermediate do you have in an SN1 reaction? Is it going to be a cation, an anion, or a radical? Cation, exactly. So when we're taking, when we're looking at benzyl groups versus alkanes, for example, so SN1 reactions are going to occur more rapidly than alkanes, and the reason for that has to do with that benzyl cation, okay? Again, very stable because we know that there's resonance stability there. So, for SN2, it's also going to, a benzyl system is going to undergo this more rapidly than an alkane as well. But there's two reasons for that. So one has to do with lack of steric hindrance. And I know you have a big bulky benzene ring, but basically they're looking at the fact that you're substituting on the methyl group. So the benzene ring isn't necessarily going to affect where you can attack on that carbon. And then again, you're going to see this coming up again and again. The benzyl system has a more stable transition state due to what type of stability? Resonance. If you haven't gotten sick of resonance, you will get sick of resonance soon. The next piece, actually, Amber, you brought it up. This is a little bit more specific, but it's talking about benzylic anions. So because we know these hydrogens are very acidic, okay, when they dissociate, we can end up with a benzylic anion, which has electrons. Basically, the proton, the H plus, has come off, leaving its electrons behind, giving it a negative charge. So the fact that we know that these are acidic, we know that we can form anions pretty readily as well.
What does more rapidly mean for both of those?
So it's in comparison between a benzyl group or a benzyl system and an alkane. So if we were going to do an SN1 reaction with an alkane and an SN1 reaction with a benzyl system, the benzyl system would occur at a faster rate. So both of them go at a faster rate than alkanes, an SN1 and SN2, but for different reasons. So I think that's the important part to remember. Okay. Any other questions about these two types? When he talked about oxidation, did he mention specific oxidation agents, reagents?
I don't think for this chapter.
Okay. We'll just briefly go over it. It's just that the fact that they bring up 3 different types, so I wasn't sure if he made an emphasis of that or not. These are just 2 different examples. Okay, so one of the types that he talks about is potassium permanganate. I don't know if you guys have ever used this. It's a very dark purple. It stains very easily. If I told you that this was a strong oxidizing agent, what might you expect the final product in this to be? Or the final functional group, I guess, if this is a strong oxidative agent.
Carboxylic acid.
Carboxylic acid, exactly. So this has fully oxidized into its most oxidized form. We'll be using the same type. Chromium trioxide. Even if you had the same starting product, this one isn't considered as strong of an oxidative agent. So instead of a carboxylic acid, we might end up with something like this. What functional group is that?
Ketone.
Ketone. Good. And the one that has a little bit more information on it. So this is a functional group that you should just understand by name and not get confused. So this is called a benzyl alcohol or a benzylic alcohol. It's important that you don't get this confused with this, right? What's the common name for this?
Phenol.
Phenol. So benzylic alcohol, the alcohol group is on that benzyl carbon, okay? So these, very specifically, can react with an oxidizing agent, manganese dioxide, I believe is what that one is. This is the only, benzylic alcohols are the only type that are going to react with this type of oxidizing agent, and you're always going to get ketones. The reason that I think that's important, because there is a practical element to this, so this reagent can be used as a test to see if a solution has any type of benzylic alcohol in it. So this one does have some practical applications. For these, I would just know that this one is considered strong, and so if you have a strong oxidizing agent, you're going to expect something oxidized to a carboxylic acid.
So would the potassium permanganate be strong and the other two be like mild?
I'm assuming based off of the final product here. This one I definitely know is considered a more mild oxidating agent. I'm not sure if this would really be considered strong or not, but I'm assuming because you only get a ketone, it's not. I'm just not 100% sure. Good questions. Okay. So this next section is talking more about phenol. Okay. So if we have So here we have phenol in its typical form. Because we have this ending, right, we know that this is the enol form of this. We have a carbon-carbon double bond right next to a alcohol group. So knowing that we can do Keto-Enol Tautomerism, this can technically be broken and reformed into this. Here we have our ketone group, so this would be considered our keto form, okay? So I've given you a couple hints here, and based off of your knowledge of resonance, which one do you think is the more stable form? Okay, why would you think that?
Because the electrons can delocalize.
Exactly. So we have resonance stability here. Because we have an aromatic ring. By moving and breaking the bonds here, we've removed the aromaticity here. We don't have alternating double and single bonds, which means we don't have resonance. You can also tell by the equilibrium that I have here. There's a much larger arrow pointing towards the phenol or the enol form. So that means that this is really the more stable, but absolutely, resonance is the main driver of that. So this is different from what you learned when we first talked about keto-enol tautomerism, right? Typically, in most molecules, the keto form is considered more stable. But because we have an aromatic ring here, this is really going to be much more stable. So definitely something to kind of separate in your mind, especially once you get closer to the final, right? And you have both this and that previous chapter to kind of have in the same, on the same exam. Okay. So looking at our phenol, our enol form, do we think that this is going to be typically acidic or not very acidic? Is a hydroxyl group an activator or a deactivator?
Activator.
Okay. How do you know it's an activator? What are the rules? Anybody remember? Okay, let's do a quick.
Oh, is it the that it's connected? The electronegative group is connected directly to the ring.
That does have something to do with it. Yep. So for activators, okay, there are basically two different ways that you can be a ring activator. You can be an alkyl group, which you just have to memorize, or you can be an electronegative group directly attached to the ring, and the last piece, you have to have lone pairs of electrons. Sorry for the handwriting. So let's take a look. So we know that oxygen likes to make 2 bonds, but tends to have 2 lone pairs of electrons, right? That one's a pretty easy one to remember. This becomes important when you get into something like activator or deactivator.
Deactivator.
As activator.
It looks like an activator, right? Because nitrogen we know is an electronegative group. It's directly attached. The hardest part is you need to know whether there's lone pairs of electrons here. And the only way to do that is to know the Lewis dot structure for this, which is essentially there is technically a lone pair of electrons, but that pair of electrons is what's used as the bond.
Why is there a double bond between?
It's a resonance structure, so this can be drawn a couple different ways. So this nitrogen actually doesn't have any lone pairs of electrons. So this nitrate group is actually considered a deactivator. That is probably the hardest example. He may use it just for that reason. But the rest of them are a little bit easier to pick up. This is really the only one that you have to know the specific Lewis dot structure for it. But taking a step back from that review. So knowing that this hydroxyl group is an activator, right? So these electrons are flowing into the ring. What does that mean about this hydrogen? If the electrons are flowing into the ring,
It's going to become weak and fall off.
exactly. So with the electrons flowing this way, it weakens this bond, makes it easier for this hydrogen to dissociate, which means that phenols are extremely acidic. I believe the term Dr. Cosper uses, unusually acidic. So here we have a typical phenol with no other substituents, and then we have a phenol with 2 nitrate groups, which we know are ring deactivators. And then we have another phenol with 3. So the concept that Dr. Cosper wants to get across is how these substituents are going to affect the acidity. So a typical phenol with no other substituents is going to have a pKa of 10.26, for example. When we add on 2 nitrate groups, that's going to drop down to around 4. Adding 3 nitrate groups, it's going to drop down even lower. So based off of this, which one of these would be considered the stronger acid?
The last one with the 3 nitrate groups?
Exactly. So whenever you have ring deactivators on a phenol, that's going to increase the acidity.
Is that the same for all deactivated groups? Or all deactivated groups?
Yes.
Or-
Yes. Because essentially what they're doing, so the activator is donating its electrons while the nitrate groups are pulling on those electrons. So the electrons are all being pulled away from that hydroxyl group. So this next section is talking about preparing phenol, and there's a specific type of reaction. It's referred to as nucleophilic aromatic ipso substitution. Essentially what's happening here is we are going to do a substitution for something other than a hydrogen. So the example Dr. Cosper gives, okay, say we have a halogen on a benzene ring, and we have a couple withdrawing groups. These withdrawing groups are important. This reaction won't take place unless you have some sort of electron withdrawing group in these positions. It has to be ortho or para. So our chlorine is going to be our leaving group. We know that halogens typically are good leaving groups. When that chlorine falls off, we're going to have a nucleophilic substitution occurring in that same place. So our nucleophile in this case could be a hydroxyl group, right? We know that a hydroxyl group has a negative charge. It could attack the benzene ring. And then if it was an OH group, your final product would be a phenol. I think that's really what you want to know here. So we didn't replace a hydrogen, we replaced a chlorine. You have to have electron withdrawing groups. And a nucleophile is going to be replacing whatever the leaving group is. This next one, I don't know how much of a focus he gave on it. I think really the important piece is the intermediate. But when we have a halogen on this type of aromatic ring, another term for it is haloarenes. It's similar to, it's just another suffix for aromatic. So if you do see that, don't get confused. It's just something along these lines. Under really high pressure and temperature, we can get this to react and perform a substitution, but it forms a very specific type of intermediate that you could be tested on. So I know my marker's kind of crappy, but can everybody tell that this is a triple bond here? Okay. What do you think, or what would you expect the ending of this type of functional group to have that has a triple bond in there? Ine. So this is referred to as a benzyne. YNE, right? Like an alkyne. This is a Benzine Intermediate. Once that's formed, you can technically go through your substitution. So say we wanted to substitute this with a nitrogen-based functional group. What's the term for a benzene with a NH2 bonded to it? Aniline. If you're having trouble with these benzene derivatives, I would definitely take a look at whatever chapter you came in on. Was it 16? 17? 15? So we've talked about Phenol, we've talked about aniline. There's also toluene. So just keep those in mind. They're going to keep popping up. You could get tested on them for this chapter. Okay. So haloarenes, aromatic rings with halogens attached to them, don't typically react under high heat and pressure. They can form Benzine Intermediates, which is just a benzene ring with a triple bond. And then you can form specific types of substitution. In this case, we're looking at an aniline being formed. Any questions on this one? Everybody good? Okay. So going back to phenols. So because we have an alcohol group, okay, we know that alcohols can act as acids and as bases, okay, so it can be protonated and deprotonated. What type of ion is formed when you protonate, when you add a hydrogen, this OH group? Or what charge would it have?
Positive.
Positive? Anybody remember the specific name? This comes from a different chapter.
Cation.
It is a cation, but a more specific name when you have this OH2 group.
Conjugate acid.
I see what you're saying.
It has onium at the end.
It does have onium at the end. I'm sorry. So this is a Phenol Oxonium Ion. Which is very close to, now I'm blanking on the original name.
Is it alkyl oxonium?
Yes, thank you. So, Alkyl Oxonium Ion, obviously, this is just coming from this name here. So here, because we're accepting a proton, this alcohol group is acting as a base. It's important to know that these are considered, because they're very strong acids, they're only considered, very weak bases.
So they're strong acids.
Yes, very strong acids. This kind of goes back to what I was just talking about. So knowing that this OH group is an activator, where is it going to direct substitution on the ring?
Oh, orthopara.
Orthopara. So because it's an activator, we would expect substitutions at any of these three places. Is there one place that's maybe favored over the others?
Para.
Why para?
Steric kindred.
There we go, yes. So by reacting at the parasite, you can prevent any steric hindrance interactions. That's really all it says there. Okay. Did he talk about bakelite
Yeah.
in class? Okay. So essentially, this is a very long process, but you can start with phenol. And react with this. How would we name this? Using IUPAC naming.
Formaldehyde.
What was it?
Formaldehyde.
So that's the common name. What's the IUPAC name?
Methane.
Phenol.
Methanal, right? So
Oh, yeah.
But good. Methanol or formaldehyde. I'm just saying that because he could technically, I have a feeling that this is going to be a longer question and it's a fill in the blank. So he might describe the actual reaction. So he could say, you know, phenol reacts with formaldehyde, or he could say phenol reacts with methanol. Right? Both of those are up for grabs. So there are multiple steps. There's Michael additions, there's methylations, but essentially your final product is something referred to as bakelite. And I spelled that wrong. This was considered the first polymer, which is why he's talking to you about it. There is an intermediate that I think he might ask you about. So during these multiple process, you make something called quinomethanes. Do you guys remember him mentioning that in class at all? No?
Yeah.
Okay. All right. So these are the reason that I think he mentions them. Alpha, beta, unsaturated carbonyl compounds. There are some other details in here, and he might have gone into more detail in class. I think this is a very brief description that covers the majority of the important information. Like I said, in his question, he might talk about, you know, the fact that there are Michael additions. So that might be another clue as to what he's referring to. But he could ask about, you know, what type of intermediate is formed, what's the name of the final product, you know, what are the two starting products. He could pretty much ask you at any point of this, but I do have a feeling he's going to describe the reaction to you in a question, because that's typically what he does.
What's a phenoxide ion?
So we just talked about phenol oxonium, right? Okay, so if we think back, alkoxide was the other type, that negative ion, right? So if we deprotonate phenol, this would be a phenoxide.
Okay.
Okay, so we deprotonate it, leaving it with a negative charge.
Would that, so that's another intermediate too?
Yes, that's true. Because this is what undergoes the Michael addition. So he could bring that up as well. That's true. Any other questions? Two more. Okay, so we have a phenol with two alcohol groups. We can perform oxidization. Oxidize this until we get to something that looks like this. I don't think that this would be necessarily a functional group that you'll have to draw, but I think the terminology could be used up. Could be used. So here, this is referred to, we have a diketone, right? That's kind of the general name for it. The more specific name that I think he could use, benzoquinones. So definitely, I mean, that could come up on your exam or your quiz. the last two pieces are more of practical uses for these types of molecules. So phenols can be used as preservatives. So there's a specific preservative referred to as BHA, or BHT is another phenol-based group. These are referred to as antioxidants. Okay, so when they're added to food, okay, they prevent oxygen in the air from oxidizing the food. When we think of food spoiling, that's what's actually happening. The food is being oxidized by the air. So when you take a bite of an apple and you leave it there and it turns brown, that's oxidation. So by adding antioxidants, we can prevent the food from spoiling. So these are two types of phenol-based antioxidants that can be added to food. There is another reaction, which is kind of the last thing on these notes. We can discuss the reaction, but I think the important piece is what's actually being formed, because it's another practical use. So we have Daizo Coupling. I'm not going to go through all the functional group names because I don't think that that's going to be his focus. But essentially, you can react a phenol with, this is referred to as an irene diazonium salt. Again, I don't think that you need to memorize that. These two react, and you end up with something that looks like this. So coupling, we're pairing these together. Again, don't need to worry about this structure, but this is referred to as an azo compound. Also known as a diazo dye. And these can be used, this is what's used to dye like clothes. So I would know the name of this reaction as diazo coupling. I would know that it makes diazo dye. I would know that phenol is involved. This is an electrophilic aromatic substitution, so that's another detail that he could test you on. So diazo coupling, we have an electrophile reacting with phenol, forming a diazo dye, which is used in the textile industry. Any questions on this one? Some concepts you see come up again and again. Pretty much every type of reaction that occurs with these benzylic systems, it's able to do so based off of the fact that it's so stable because there's so much resonance. So you'll see that come up again and again. Again, knowing these names because they can come up, so the toluene, aniline, phenol. And I would definitely review ring activation and deactivation because that's going to come up again.